Hello! If you're joining me on the day of the regularly scheduled lecture, it is Wednesday, March the 4th, and you're probably thinking about finishing up your participation in the fever discussion, hopefully if you took part in that extra activity, and we'd like to try to finish that up, all of our interaction by Sunday. With regards to homework 5, this will be your last homework prior to the second exam, so remember to get that done and submitted on March the 10th. So just hopefully beginning to think about getting it started and maybe trying to get the first few questions clicked off the list. Speaking of clicking things off the list, it is about that time to get your skill assessment rubric done and turned in. In fact, it will be due on the week of March 9th through the 13th, and on that week you only have one attempt. So try to get at least one attempt done now, and if you're not happy with that first attempt, then you can take the week of March 9th through the 13th to do a second attempt. So that being said, let's jump right back into our riveting coverage of metabolism. This page in your notes allows you to review the chemical makeovers that the molecules in glycolysis or the Ebden-Meyerhof pathway undergo. Of course, we can watch the gradual oxidation of the glucose molecule through time and eventually seeing the very highly oxidized pyruvate molecule. And in fact, those of you who really like to dork out with chemistry may even want to take a moment to draw out the structures of some of these molecules. For example, our epic pyruvate molecule being a very highly oxidized molecule, lots of bonds to oxygen, and this is its full glory structure. And you could do that with each and every one of the molecules. Of course, we've many times done that with glucose. So the other thing that you'll probably want to do and practice on this page in your notes is adding in the ATP input and output. So for example, we know in the first step of glycolysis, ATP is infested as glucose is phosphorylated to make glucose 6-phosphate. So you could add in all of the investments and just use this page to allow you to become more fully intimately acquainted with the molecular rearrangements and oxidations that are occurring within the process. Now, that is the most important thing about learning metabolism. That is, you need to actually draw it. You need to draw it and then draw it again and then draw it again and then draw it again and keep on making and synthesizing your own learning tools. So towards those ends, one of the things that I want you to do is to begin to make a poster. And on that poster, I want you, and I'm going to go ahead and show you a version of my poster. I want you to have a sort of big picture view of how all of the steps in metabolism come together. And in a moment, I'm going to show you some student posters that are epically cool. In my poster, I've used a yeast cell as my organism, my model organism, to make a very nice view or look at all of glycolysis. At this point, that's the only pathway that we've learned is the Ebden-Meyerhof pathway. So on this view, you can see that the processes do take place in the cytosol of the yeast cell. So it's cool to make a poster like this because it can enable you to see where all of the different processes take place, see their compartmentation. Of course, we know that this is a eukaryotic cell because we've got our mitochondrial matrix here where eventually much of our action is going to take place. My poster is incomplete right here because I haven't added on some of the details. For example, of course, we remember in step 1 that ATP is consumed. And again, in step 3, we know in our epic pour-off step where catalyzed by phosphofructokinase, ATP is once again consumed. For us being in the hole at -2, and then we've got our splitting of something sweet step 4, step 5, that equilibrium step 6, finally netting some pay dirt in the form of NADH, and then once we get our 1,3-BPG, remember that that is able to transfer a phosphoryl group onto ADP to make ATP, and in fact stoichiometry is 2 here, and now we get 2 ATPs, we're out of the hole, we've now net 0, but then when we get to this PEP, the wicked high energy phosphoenolpyruvate, we see the transfer of a phosphoryl group onto 2 more ADPs to finally net us that 2 ATPs. and give us the pay dirt that we went in hoping to get. And of course, reducing power N, ATPs, and pyruvate in a ratio of 2, 2, and 2. So this review is super important. Let's take a look at some of the other student posters. So let's check out some of this other students' posters, and you can see this one behind me is larger than life. You can see the donut getting oxidized in glycolysis, so you can see that this was done on a shower curtain. So you can choose your shower curtain to make your poster. You can see the glycolytic pathway here, glucose 6-phosphate, fructose 6-phosphate, the ever epic fructose 1,6-bisphosphate. Now this student could have added some details by adding enzyme names and structures. You can add anything you want on your poster, and guess what? You get to use it on the exam. So this is definitely something that you want to start making and you want to put a lot of effort into. So let me show you some sweet other student posters. This one is pretty cool. You can see the glycolytic pathway over here, Ebden-Meyerhoff. You can then see that they've added the other alternative glucose degrading pathways on here as well, and you can see where the electron transport chain, TCA cycle, and all of the other jazz comes into play. Pretty cool poster. One of my absolute favorites right here. This student is super creative and was able to find a way to come up with putting all of the different pathways onto one cell that he's made into a fictional cell. Of course, remember that the etnoduteral pathway doesn't necessarily take place in the same kinds of cells as does the Ebden-Meyerhoff, and we'll be talking about that more. But this is a wicked cool poster as well. So begin to think about how you're going to make your poster. Start to see it take form. Rewrite and write and rewrite and do it in pencil, and then trace over it in pen when you finally know that you've gotten what you want. So these are going to be your epically awesome tool for the exam. So get them started.
Oh my god, Benny, look at those donuts. They have so much glucose. Like, can you imagine the potential energy? Like, ATP, NADH? I mean, it's just gonna be ripped and stripped of high energy electrons. Who doesn't want a donut, okay? I mean, glucose is just so sweet. I mean, literally, duh. And it's like totally awesome. Look, glucose is just so bitchin'. I like glucose and I cannot lie, and my classmates can't deny that when a girl walks in with a donut in her mouth and a ramping head south, it gets metabolized. Wanna break it down, and hexokinase goes to town. When glucose enters a cell, it rejoices more than Adele. Enzymes freak out, and I say that without a doubt. My teacher tried to warn me, PFK is vicious and ornery. To hell with hexos, bring it on now, 2 times trios. Then use me, cause you ain't just an average whoopee. Make some PEP, cause it's high in energy. But stop, revert, we forgot about the pay dirt. Hear about reducing power, more punch than a whiskey sour. To the average donut and ask it that, you're a big fat cat. So Bellas, has donut got some glucose? Then shake it, shake that sprinkled donut. Baby got glucose. Baby got glucose. Yeah, baby, when it comes to glucose, proteins ain't got nothing to do with my selection. 32 ATP? Yeah, thanks to the ETC.
once you have a really nice poster, you'll find it easy to do challenging questions, even those questions that are a little bit mathy. Let's try one. This one is very straightforward, but sometimes just seeing the math seems overwhelming to people, and seeing big numbers. So let's see if we can take this on and totally rock it out. So if 3.34 times 10 to the 21 molecules of glucose are oxidized by a culture of bacteria living on a GSA plate, remember that glucose is the source of organic carbon in a GSA plate. So glucose will be oxidized in pretty large amounts on a GSA. This number of molecules is representative of the kinds of amounts that you would find in a GSA. How many net ATP molecules are harvested via substrate level phosphorylation in the Ebden-Meyerhof pathway only? How much reducing power is created? So this is where we just have to remember our output. Remember that for every time the Ebden-Meyerhof pathway runs, for every glucose it degrades, 2 ATPs are made. So we just need our trusty conversion factor, 2 ATP per every 1 glucose. And hey, you're setting it up right now to cancel some sweet units. So just multiply it by the number of molecules of glucose, 3.34 times 10 to the 21 molecules of glucose. And excellent, we get to cancel units. It feels so good. And we can get 6.68 times 10 to the 21 ATPs being net. Now, it shouldn't be terribly hard to go from there to get the number of NADH molecules, because of course we recall that the stoichiometry is the same. There are also 2 NADHs yielded for every 1 glucose molecule that is oxidized in the Ebden-Meyerhof pathway. So I'll let you finish off the math on that one. We need to now proceed along to talk about an alternative glucose degrading pathway. This pathway is called the pentose phosphate pathway. I kind of like its alternative name, the hexose monophosphate shunt. And I'll show you why I feel like that is a very descriptive name for the pathway. So the hexose monophosphate shunt. In this pathway, I'm going to label it by both of its names, the pentose phosphate pathway or hexose monophosphate hexose monophosphate shunt. We might also say, if you would like to add more parentheses here, that this is another glycolytic pathway. This is a second glycolytic pathway different than the Ebden-Meyerhof pathway. And it's run at different times. Remember that the Ebden-Meyerhof pathway has as its central goal the production of ATP. That ATP can be produced directly by substrate level phosphorylation or indirectly by making high energy reducing power that can go to the ETC. But that is the goal of the Ebden-Meyerhof pathway. The goal of the pentose phosphate pathway is very different. Instead, this pathway has as the goal to support the synthesis, the biosynthesis of molecules. That is, to support anabolism. So said another way, we might say that the pentose phosphate pathway is run when a cell needs to build stuff. So let me just put an arrow and say this pathway is totally upregulated when a cell needs to build stuff. Or said a little bit more in a more sexy vernacular, we could say upregulated when a cell needs to build stuff, or AKA when a cell is focused on anabolism. So in a cell that is actively replicating and needs to synthesize a great deal of DNA, that would be a wonderful example of a cell that would upregulate the pentose phosphate pathway. That makes you start to think about the kinds of products that might come from the pentose phosphate pathway. That is, products that will support anabolism. For example, remember that the reducing power in the form of NADPH is the type of reducing power that is utilized to provide electrons to anabolism to reductive anabolism, right? It brings the reducing power to reductive anabolism. So we better darn guess that the primary product of this pathway is NADPH. And in fact, the entire first stage of the pentose phosphate pathway is just dedicated to making lots of NADPH. The second portion of the pathway is dedicated to synthesizing ribonucleotides. That is, it is dedicated to making the subunit ribose 5-phosphate to enable the synthesis of DNA and RNA. So the second stages will have that as their central goal. Just like glycolysis or the Ebden-Meyerhof pathway, this occurs in the cytoplasmic matrix. It can operate at the same time as the Ebden-Meyerhof pathway so that the cell is both giving off ATP but also the reducing power needed for anabolism. So some molecules of glucose 6-phosphate might go on in the Ebden-Meyerhof pathway, whereas some of them might be, here we got it, shunted off over to the pentose phosphate pathway where they can be utilized to make NADPH. Again, just like glycolysis or Ebden-Meyerhof, this can operate either aerobically or anaerobically. That is, it is completely, it could care less about whether or not oxygen or a terminal electron acceptor is present. It does not rely on that. We're not going to memorize all of the steps of the pentose phosphate pathway. However, you do want to add it onto your poster. Let's look at the broad stages of the pathway and hone in on the goal of producing first NADPH. NADPH is the primary goal of the oxidative stage. And in fact, this molecule is produced in oxidation reactions that occur in step 1 and step 3. NADPH is produced as the primary product here, and the ribulose 5-phosphate might go on into further steps to make ribose 5-phosphate, or if the cell just needs NADPH, the ribulose 5-phosphate can be recycled, and we'll see in a minute how that happens. I thought it might be of interest to several of you, Jeff, DJ, Trey, all of you might be interested in the fact that the first enzyme that catalyzes this, step number 1, as you might all guess, is most likely to be a regulated step. Notice a metabolically irreversible step, a step whose enzyme is most likely subject to feedback inhibition, feed-forward activation. But it's also really interesting to note that in humans, that if this enzyme is deficient, then the cell's ability to keep iron reduced at the active site of the hemoglobin molecule is deterred, and that leads to sickle cell. So it's interesting to see the root of that deficiency and the cause of that disease. So the oxidative stage has that goal of giving up electrons in the form of NADPH. The NADPH can now run off to power anabolic reactions, reductive biosyntheses. If a cell is focused on making DNA or RNA, it will convert this ribulose 5-phosphate into ribose 5-phosphate in the next stage. These are the non-oxidative stages of the pathway. And if a cell needs lots of ribose 5-phosphate, making lots of DNA, for example, then the pathway is completed here. However, if a cell needs tons of NADPH, maybe in helping to keep a metal ion reduced like iron, but it doesn't need a lot of ribose 5-phosphate Legos, then in which case it might actually not need ribose 5-phosphate, and instead the intermediates such as ribose 5-phosphate will be recycled and converted back into molecules that you will recognize. These molecules are glycolytic intermediates, and you will for sure recognize glyceraldehyde 3-phosphate, fructose 6-phosphate being intermediates in glycolysis. So now these can be shunted back into glycolysis. And that's why, again, the hexose monophosphate shunt is a really fitting name for the pentose phosphate pathway, because remember, glucose 6-phosphate is the first intermediate of the Ebden-Meyerhof pathway. It's getting shunted over to make NADPH and ribose 5-phosphate, and then it's getting recycled back, and the products are getting shunted back into the Ebden-Meyerhof pathway. So it's like this, it's a detour. It's like the hexose monophosphate shunt is a temporary detour in order to make NADPH and ribose 5-phosphate. So we could actually look at this on our big picture poster, and I do highly encourage you to add this onto your big picture poster, even if it's not with all of its details. It can be with more or less detail as you see fit. And I'm going to jot it down with slightly less detail just for purposes of fitting it on my poster. So what we would see going on here is that the glucose 6-phosphate gets shunted off into the pannose phosphate pathway, which I'll just call PPP for short, just to fit onto my drawing. And then we know that the two products that might come out of the pannose phosphate pathway will, of course, be lots of reducing power in the form of NADPH, which can take its reducing power to power anabolism, and also ribose 5-phosphate, which we know is a building block in DNA and RNA synthesis, nucleic acid biosynthesis. But if that's not needed, then we also know that the intermediates can get siphoned back into glycolysis in the form of fructose 6-phosphate and in the form of glyceraldehyde 3-phosphate. One question that I commonly get from students is, why wouldn't a cell just run the PPP all the time? I mean, it looks like it makes sense because all of the intermediates of glycolysis enter back in before we get any pay dirt. So why not get the yield that we would get from the pannose phosphate pathway first and then get the yield that we would get from glycolysis? And it's a great thought. The only issue with that is that for every time a glucose 6-phosphate goes to the PPP, there actually is the loss of a CO2. So if 6 molecules of glucose 6-phosphate get shunted over here, we actually lose a full molecule of glucose. So there is a price to be paid, even though it seems less obvious, for running the pannose phosphate. So a cell would only want to run the pannose phosphate pathway if it needed NADPH and if it needed ribose 5-phosphate, or if at least it needed one or the other. So that being said, that is an alternative glycolytic pathway, different from the Ebden-Meyerhof pathway. And now we only have one more of those pathways to talk about.